All right, howdy everyone. We'll get started. That's recording. Okay. So welcome. Today will be the second to last review session of the semester. We'll have a final review today, and then Monday evening, I think, will be your last review session for like just last minute questions. Probably around like 7 o'clock, 7 to 8 or something like that. So I'll set out another announcement with a Zoom link probably Sunday so that you can join that on Monday for any last minute questions you may have before your exam on Tuesday. And then you're all done. Yay. So that's my plan for that. And then today I have the mock exam if you want to go over the mock exam. Or if you just have like general review questions or general topics you want to go over, I'm happy to do any of that. So yeah, the floor is yours. I'll let you ask your questions away. Anything specific you want to go over today? I can also just like throw some questions at y'all. See what sticks. Do we feel okay on the most recent topic that Dr. Bengali lectured on? Yeah, for sure. So when we look at delta G, we know that delta G, hello? So when we look at delta G, we know that delta G, why is this not working? One moment. My iPad is frozen. Good. Let's try that again. Mhm. Okay. Yeah. So when we talk about delta G, we know that a negative delta G means that it is spontaneous. And if we have delta G that is positive, right, equal and opposite, that is non-spontaneous. So when we're looking at delta G's, we can also look at K's. So for a K, we know that K equilibrium constant, if this is greater than 1, then that means it is product favored. And if K is less than 1, then that means that this is reactant favored. So if something is product favored, then we also know that that is spontaneous. So if K is greater than 1, then that relates to this top form of delta G. And if we are related to K less than 1, then that relates to this K being positive, or delta G being positive. And how that relates is through the equation delta G naught is equal to negative RT ln of K. Since we had that natural log, if K is greater than 1, that will make the natural log positive. If we have K less than 1, then that makes the natural log negative, and then that takes that negative in the front, making delta G positive. Okay? So if you're given equilibrium concentrations, right, then you can just solve K and then solve delta G from there. So as an example, okay, so let's look at this one here. We have considered the reaction where the equilibrium concentrations are as follows, and we have the concentration of H2 is 0.6, concentration of N2 is 0.4, and the concentration of NH3 is 1.2 times 10 to the negative 3. Okay, and we're given the reaction where ammonia breaks down into nitrogen and hydrogen. Okay, so what do we need to solve for first if we're trying to find, oh wait, I didn't finish my question. So what is the delta G naught of the reaction in kilojoules per mole, right? So we first need to, if we're trying to find for delta G, we need to figure out how can we relate equilibrium to delta G. Yep, so K is products over reactants, and then you plug that into delta G. So we'll first do K. That's N2, and this is H2, 3 over NH3 squared. So that will be okay, so we have K equal to 55296. Is this a big K or a small K? What is favored here? Products or reactants? Yep, so this is big K, so this is product favored. So are we expecting a negative or positive delta G? Good, we are expecting a negative delta G. So then we can take that and plug that into delta G naught is equal to negative RT ln of K. If I don't give you a concentration, or sorry, if I don't give you a temperature, just assume 25 degrees Celsius. What R value are we using here, the big one or the small one? Yep, we're using the big one, and that's because 8.314 is in joules per mole Kelvin. So we're trying to get to kilojoules per mole, so we need the energy component or the energy unit in our delta, or in our R. T is going to have to be in Kelvin, so that'll be 298 Kelvin. That's 25 plus 273. Take the ln of our K. This is in joules per mole. So this will go to negative 27.1 kilojoules per mole. Okay, Hunter, does that answer some of your questions on delta G? Not Hunter, Warner, does that answer some of your questions on delta G? Great. Okay, and then just to wrap this portion up as well, right? We also have the other equation where delta G is equal to delta G naught plus RT ln of Q. So this is when we're not at equilibrium, right? So if I gave you non-equilibrium conditions, you could do the same thing. You would plug this delta G in for delta G naught, and then you'd be given other conditions. So let's say yeah, right. So you could do these conditions. This is not at equilibrium, but at 25 degrees Celsius. And you could solve for delta G, not delta G naught, and under these conditions. Okay. Yep, perfect. Okay, so we have consider the reaction given, and we have delta S and delta H values, and we're looking for delta G. So does anyone know of the reaction or the equation that relates delta G to delta H and delta S? What are we looking for there? What were they? Yep, so we have delta G is equal to delta H minus T delta S. And how do we solve for delta H and or delta S given the conditions that we are given here, or given the values that were given here? How would I ask her, or how would you solve for delta H of formation? Perfect, right? So for delta H, And for delta S, we can do the sum of the products minus the sum of the reactants. Okay, so we can take our delta H of formation. We have to remember that the reaction has to be balanced in order to do this. So for delta H, we'll take 4 times the NO2, which is 33.15. Do we need to do anything with the oxygen for delta H? Right, that's 0. So we don't need it because our delta H of formation of something in its elemental state is always 0, right? It exists that way. We don't need to form it at all. So that'll be just our products. And then for our reactants, we have 2 times 13.30. So for delta H, I got 106 kilojoules per mole, I think. Yep. Okay. And then we're going to do the same thing for our delta S. However, this time we do need to include the oxygen because, oops. We do need to include the oxygen because that does have entropy associated with it. However, this time, all of our entropy is in joules per mole Kelvin, right? So we do need to make sure that or pay attention to the fact that our units are different. So I get delta S naught equal to 453 joules per mole Kelvin. Hey, any questions on how we found delta H or delta S? Right, then we can plug that into our big delta G equation. So then we'll have delta G naught is equal to, these are all in kilojoules, so I would probably convert my entropy to kilojoules. So I would have 106. I guess these are also just kilojoules. Sorry. We're given 25 in our questions. This would be 298 Kelvin and then 0.453. Because I'm taking my joules and converting that to kilojoules. And I get delta G naught is equal to negative 28.994 or negative 29 kilojoules. That's going to be at C. Yep. And then just a couple other questions that they could ask you from this one, right? Something similar, but the same concept. They could ask you when this reaction would be spontaneous. So, right, you have a positive delta H and you have a positive delta S. The world prefers negative delta H's and positive delta S's. So in your delta G equation, you have a positive and a positive in terms of your delta H and delta S. So you can be asked, is this going to be spontaneous at high or low temperatures? When you have a positive and a positive, you want this second term to be more negative than the positive term of the delta H. So at high temperatures, this reaction is spontaneous. Right? Because then at high temperatures, that T value is getting bigger, and then you have your S value. And then, right, that becomes a very positive number, but then you're subtracting it from another positive number. So you have a more positive negative number. Yes, yep. So since you're releasing heat, that is allowing your energy of your system is lower, right? The energy of your products is lower than you're starting. So since you're releasing heat, that makes your molecules more stable because they're at the lower energy. And that just allows for energy that's being released to be used for something else. So that's why the energy or the world prefers a negative delta H. They could also ask you, when does a reaction become spontaneous? And a reaction becomes spontaneous when delta G is equal to 0. So that's when delta H is equal to T delta S. So you can find the temperature at which it becomes spontaneous, and then it could ask you for if it's a high temperature or a low temperature that it would be spontaneous at. Yes, yep, when delta G is equal to 0, the reaction is at equilibrium. Correct. Yep. And then Warner, you can access your past exams, I think on Gradescope, you're able to see them. You see your answer choices. And then you can see what questions you got wrong. And then I think Dr. Bengali posted an answer key in the announcements. So then you can compare your Scantron to the actual test question. Yep. Delta S is for entropy. Entropy is, right, disorder of something, so chaos, whatever. Gases have the highest entropy, liquids have the middle, and then solids have the least amount of entropy because they don't move. And then entropy increases with temperature. So everything above absolute 0 will always have some sort of entropy associated with it. Okay, so for question 36, we have which of the following molecules has a dipole moment? So we're looking for a polar molecule. So the first thing you want to do is you want to draw out all of the Lewis structures for your 4 compounds given here. I would do that first if you haven't done this already. I'll give you a minute to start it. And screw it. So for BCl3, right, boron is going to have 5 electrons, chlorine is going to have 7 times 3. This has a total of 26 electrons. We use 6 from our single bonds that we make. Boron has 5? Am I forgetting my periodic table? How embarrassing. Yes, 5. 21, 5, 26. Boron has 3. Good morning. Okay, we have 24 electrons, excuse me. So we use 6 from our single bonds that we're making 2 boron, and then we'll distribute our lone pairs. Boron is one of our exceptions that it is okay to not have a complete octet. It is happy with only 6 electrons to its name. So that is a valid Lewis structure, and we can keep that. That's good to go. So when we look at this, we see that we have an electron domain geometry of trigonal planar. We have no lone pairs, which means that our electron domain geometry is the same as our molecular geometry. So since we have a trigonal planar molecular geometry, this is symmetrical. Think of an equilateral triangle. And so since it's symmetrical, any change in dipoles or any change in polarity, which we would have a little bit here, would be negated because that's like tug of war at the 3 corners of a triangle. And so therefore this is a nonpolar molecule. Polarity comes from changes in electronegativity. So you would be given values if it wasn't obvious which one would be more electronegative. But right, the closer you are to fluorine, the more electronegative you are. So which of the following molecules has a dipole moment? Since we have a nonpolar molecule, it's not going to be A. So for silicon, that has 4 electrons. Chlorine again has 7. We have 32 total. I will tell you that this is a complete octet as well. I think, wait, it's 8, 24, yeah, 6, 12, 18, 12, yep. So this has all of this electrons accounted for. Silicon and chlorine do have a slight change in electronegativity. Chlorine is more electronegative. So those all pull out. For your electron domain geometry, does anyone know what this electron domain geometry is? Yep, this is tetrahedral. Since we have no lone pairs on our central atom, then our molecular geometry is also tetrahedral. And so since this is a symmetrical molecule, this also does not have dipole moment. Anything that has a lone pair will be nonpolar, or sorry, anything that has a lone pair will be polar. There are 2 exceptions, and that is the T shape and that is T-shape? No, T-shape is polar. That is linear when there are 5 electron domains, and that is square pyramidal when there are 6 electron domains. Anything else then, if you have a lone pair on the central atom, then it is a polar molecule. I can show you an example. Yep, yeah, I'll show you an example when we're done with the question. So for nitrogen, this one has 5 electrons, fluorine has 7. This is 26 total. Here we now have a lone pair on our central atom. Right here is our lone pair. Is there a difference in electronegativity between fluorine and nitrogen? Do we have electronegativity differences between the two? Yep, we do. Which one is more polar, fluorine or nitrogen? Or which one's more electronegative? Yeah, fluorine. So fluorine's more electronegative. Those are going to point out towards the fluorines. What is the electron domain geometry of our molecule here? What is 4 electron domains? Right, we have 3. Yep. We have 3 from the fluorines and 1 lone pair. And then does anyone know or anyone remember what the molecular geometry is? Good. This one is trigonal pyramidal. So I like to think of this as, right, I always think of tetrahedral as a tripod where you have your 3 feet and then you have the center and then where your phone will connect if that's like an extender. So where those pieces connect is your central atom, your phone would be the top atom, and then, right, that would be like the lone pair in this case, and then your feet are all your fluorines. So since you have a lone pair there, that's going to disrupt the symmetry of your molecule. And so since we have dipoles and an asymmetric molecule, this will have a lone pair. Your dipoles will not cancel out. And so this one will have a dipole moment pointing down. Or yeah, kind of, sort of. It will have a dipole moment. This is asymmetrical. So dipole moment in this one. F2 should be fairly straightforward. Right, that's just F bonded to F. Anything bonded to the same atom, it will never be polar. So this will not be it. It will be NF3. Questions on that one? Does that answer our question? Whoever had 36 as a question. Great. So for your exceptions, we have 5 electron domains, and that's going to be your central atom. And that's when you have a linear shape. These are both at the axial positions, and then all of your equatorial atoms are lone pairs. This is something that has lone pairs, but is still nonpolar. And the other ones, when you have 6 electron domains, this is square pyramidal, or I'm sorry, square planar. This is when you have a central atom and 4 atoms bonded to the central atom, and then 2 lone pairs. There. And these positions, your equatorial atoms are still bonded, and your axial atoms or your axial positions are your lone pairs. Mm-hmm. Okay, and then we'll do the quiz question. Okay, so for this one, we have what is the final temp after 53.6 grams of water at 31.8 degrees Celsius are mixed with 56 grams of water at 16 degrees Celsius. And we know that the specific heat of water is 4.184 joules per gram times Celsius. So when you see this one and you have two different like masses, and then different temperatures finding the same final temperature, what I want you to think of when you don't see anything with like a calorimeter or a bomb calorimeter or anything like that is Q is equal to negative Q, and that Q is equal to MC delta T. You will be able to plug in MC delta T into both sides of your equation. Any questions on that? Where that comes from or anything like that? Okay, so if you have MC delta T is equal to negative MC delta T, it does not matter which one you assign the negative sign to, the math should work itself out as long as you remember to carry it down. So your mass is in grams. So you can take your first one, we'll say this is 53.6 grams. We know the specific heat of water is given to us. And then delta T is always T final minus T initial. And then we do the same thing for the other side. Um, it technically should, right? I think it should, since it's the same on both sides. So we can probably get rid of the C. We don't need that since it's the same C. You can try it without canceling out the C, and I'll try it with the C and see if we get it to the same answer. So when you look at T final minus T initial, your T final is what you're looking for, right? We're looking for the final temp. So your initial is what is going to change for the two of them. So for 53.6, right, I'll do that math right now. Right, we have 224.26 times T final is what we don't know, minus T initial, but that 53.6 is at 31.8 first. And then we'll have negative 234.3 times T final again. We don't know what that is, but it will be at the same one. And this initial is 16. You can then distribute your values into your equation to solve for TF or X in this case. Right, remember we do have that negative in front of the right-hand side of our equation, so we need to make sure we're distributing that negative in as well. So I got 23.1. Cool, yeah. So in the beginning, since your C's are the same, those should just be able to cancel out. You're welcome. I don't think you'll see too many, if any at all, bomb calorimetry questions on your final. Those are just a little complicated and we ask you those in the quiz. So I would say something similar to this would show up on your exam. Alrighty, any other questions? I would suggest studying for this final by looking at the mock exam first, obviously. And I would do your mock exam, or I guess you won't have to be first, but I definitely look at your mock exam, and then I would treat that as like a mock final. Give yourself 2 hours to take it, go through all the problems, see how long you take during all of them, see what you know, see what you don't know. I mean, honestly, I would do that first just to see like what types of problems are being asked, what types of questions are being asked, and get you a good idea of what is happening and where you aren't proficient in the material in. And then you can go back to the other quizzes or the other exams or your other homeworks and look at those topics that you're not super familiar with from the mock exam and start like studying those a little bit more and studying some questions from there. And then, I don't know, maybe like Saturday or Sunday, try the mock exam again in another 2 hour setting and see if you're able to take your exam or at least answer the questions that you couldn't answer before in a more timely fashion. so that you are best prepared for the exam on Tuesday. So you can use that one, but we have a combined equation that you can use as well. So that one is the ln of K1 over K2 is equal to EA over R times 1 over T2 minus T1. You could do that one too. That one's actually, the one I wrote down is more straightforward and definitely easier. You tell me, are you using the ER? Are you using the big R for this type of problem? What are our units in? Yes. Yep. So we do want to use the 8.314. Dang, the wind is crazy right now. We do want to use that one for this problem. Yep. Any other questions? I would expect solving for like an order of a rate law from experimental trials, right? Like trial 1, 2, 3, and looking at how that changes. Right, to find your rate law expression there, or your rate law equation. And then I would also think that they would ask you something along the lines of relative rates or initial rates, right? If you're given that A has a rate of -2, right? It disappears at a rate of 2 minutes, 2 molar per second. Like, what is C, a product? How does that compare, kind of thing? And then I would think they would ask you some sort of half-life question using an integrated rate law to then use the half-life from there. So kind of similar to like the last question we did in lecture on Tuesday, where you solved for K and then used that in the half-life. You probably have to identify the rate law expression from like a slow step or mechanism. So I would just also be prepared for that. Enthalpy through bonds. So if you want like how much does the enthalpy of formation happen for like bond breakage? I think is the question. So when we look at something like question 32, right, these are for heats of formation. And that is looking at forming that specific compound. We said that was products minus reactants. You could be given something that was bond enthalpies. And with bond enthalpies, this is looking at how much energy it takes to break a double bond of oxygen, or how much it takes to break a triple bond of nitrogen, right? Those are all bond enthalpies, and these all have delta H's associated with them. When you're looking at this is now reactants minus products, because it is bonds broken minus bonds formed. Right? All bond breakage requires energy, all bond formation releases energy. So you want that bonds formed to release more energy than your bonds broken, right? To make it a negative delta H. So what would usually happen there is you would write out usually a non-complex molecule, right? Think carbon dioxide. We'll do the one from earlier, right? If we had NH3 forming N2 and H2, right? You would be required, or you'd have to solve for the number of bonds being broken. In this case, this is NH3. You have 3 NH bonds, but you have 2 of those molecules. So you have a total of 6 NH bonds that are being broken, and that would go into your bonds broken or your reactant side. Then you would have N2 forming, which is a triple bond, and then you would have 3 HI or HH bonds forming, and you would multiply, right, those together, and that would go on your bonds formed or your product side. And then you would just solve for the delta H that way. So it is dependent on the number of coefficients and the number of bonds in each of them. Right, you don't just have 3 NH bonds, you have 6 total because you have 2 moles of those. And then you don't have just 1 HH bond, you have 3 HH bonds. And this is the only time we see reactants minus products. Usually it is final minus initial, but in this case it is bonds broken minus bonds formed. So if you're solving for the heat of formation, HF, for the 2 HBr goes to H2 and Br2, that would be products minus reactants, right? What we did for question 32 was products minus reactants. If you're looking specifically for the bond enthalpies, right, that's what you'll see, bond enthalpies, then that would be products, or that would be reactants minus products. Because it's bonds broken minus bonds formed. Cool, great. Any other questions? Yes, MW is referring to molar mass. That is like molecular weight, molar mass. Those are the same. Yes, I would say the mock exam is pretty accurate for like distribution of exam questions. Yeah, I think that's very representative of the final exam. Anything else I can do for y'all today? Yeah, of course. All right. Well, if there's any more questions, like feel free to ask them, but if not, I'll say thank you now. And if I don't see you on Monday night, it's been a pleasure and thank you for uh coming today and I wish you the best of luck. And let me know if you need anything else. But if not, if there's no more questions, feel free to have the rest of your Wednesday and get back to something else and good luck on the rest of your finals. But if anyone does have other questions, you are more than welcome to ask them.